Testing. Testing.
Hello.
Hey, Henry, can you hear me?
Yeah, I can hear you. My computer should come tomorrow. This is my old computer.
Well, hang in there.
Having trouble opening a bank here. That's the problem.
Plus the apocalypse, you know,
Yeah.
all the little things.
It's 4 a.m. here. I put the children to bed. I fell asleep putting the children to bed, so I'm up.
Actually, I have some bad news. Our scheduled guest speaker, Marco, lost power about an hour ago. He's going to be off the grid. He won't be able to make it. So if you were staying up to see him, we'll have to reschedule that. But yeah, bummer. I'll announce that again once more people are here, but I figure we should wait for a little while.
Mm-hmm.
Howdy, everyone. It's still only a couple minutes past the hour. I figure we'll give people till about 5 past. 15 people on so far, pretty good turnout. Just a general announcement, our scheduled guest speaker, who I was super excited about, Marco Rodriguez, creator of Ticker Pop, was going to give the guest lecture about his particular applications of category theory, but he lost power at his house about an hour ago, and so can't join. We'll get his talk another day, but anyway, there are people who are joining. It'll just be the intro to CQL talk and then applications as the audience is interested in. Yep. On that note, while we're waiting, people are free to chatter amongst themselves. If we were doing this in person, there'd be pizza and socializing and all of that. Usually, I mean, mathematicians are not necessarily the most sociable, but at least that's part of the idea. So anyway, people are welcome to introduce themselves, and we'll get started in a couple more minutes.
What's the reason for the power outage?
He's tweeting about it. I put the tweet in the comments for the meetup. Actually, it's, I don't know, some kind of shenanigans with his neighbor who was digging, but in addition to not being supposed to dig, like wasn't supposed to have a house, or something. So it's like some kind
I saw that tweet, so I was just wondering whether that was the tweet I saw, and I was searching for it, but I couldn't find it.
Yeah. I don't know. There's been like a lot of police activity over where he lives lately. I mean, independent of what's going on now, like we're talking months ago. I don't know. It's that's the apocalypse for you, I guess. On that note, maybe we should go ahead and get started. There's about 18 people here, which is about what we had last time or so. So just by way of introduction again, today I'm just going to give the introduction to category theory for databases and then talk about applications of category theory as the audience is interested in. Our guest speaker got waylaid. We had to reschedule him. So it'll just be this talk. So probably about an hour or so of material based on what the audience wants. And then, yeah, so with that in mind, I'll go ahead and get started unless anyone has any questions or just wants to introduce himself to the group before we begin. Cool. Okay, so hopefully everyone can see the screen. So this is the, actually I'm happy we're recording this because there's been other versions of this talk that, there always seems to be some kind of technical difficulty. If nothing else, the pandemic is a good excuse to get good master copies of lectures down. But anyway, what this talk is, it's an academic talk that I'm trying to give to a more, or just pick the introductory parts of, but it's a talk about how to use category theory to do data management. And so, we often talk about, how our approach is algebraic or categorical, and, we'll get into all of that. But basically the key insight is that category theory, this branch of math that we all have come to know and love, has been very successfully used to migrate theorems from one branch of math to another, right? So category theory was basically invented to transport theorems in topology to theorems in algebra, for example. And so the thinking here is that if you can do that kind of thing with knowledge in the form of theorems, then you should be able to do that kind of thing with knowledge in the form of data, right? Like database tables and facts about the world. And so we refer to that as functorial data migration, and we'll talk a lot about it, but that is the analogy, right? That if category theory can connect branches of math, it should certainly be able to connect branches of your IT infrastructure together, right? And so research has been productive, but slow since its research. So this project started about 10 years ago. It was started by David Spivak and a few others at MIT. We spun a company out of MIT to commercialize the work. There's an open source version of the tool, which I'll demonstrate today, called CQL, that you can download. And I'm sure most people here have probably played around with it in any case. But yeah, that's the where we are, the state of the world. And so the point of view, or the point of this talk, is that I'll talk a little bit about category theory, just not like at the level I've been doing with some of the other talks, like, you know, going to into textbooks, but I'll just give a review of some of the basics, talk about the categorical query language, which is really just the how to manipulate databases using category theory, demonstrate the tool, and then with the time we have left, I can talk about whatever the audience is interested in, be it more on CQL, arbitrary category theory, that type of stuff. So any questions before we get started? Cool. Okay, so there's a number of ways to apply the insight of category theory to databases. In this talk, and I'll be describing one way, which is through our CQL tool, and it is a tool of a particular class of tools called ETL tools. And so these are tools that do extract, transform, and load on data. They do data migration. And so systems that do query are a special class of ETL tool, where you're doing kind of a degenerate extract and a degenerate load in like a very precise type of transform. But basically, we'll be talking about how to use category theory to either move data from one schema to another, or integrate data from multiple databases. But that being said, there is, of course, a lot more stuff you can use category theory to do, right? Our friends at NIST have a paper about how to use category theory on music, right? You can use it to do all kinds of interesting things. But you know, for the purposes here, we're going to stick with our ETL data migration-ish type of viewpoint. And I should mention this includes what, you know, I say ETL and data migration, but just because of how the math works out, that includes what some people might consider data integration as well, data warehousing. And so the examples that we've completed with this tool have both a data integration and a data migration feel. And so in this talk, I won't get too much into the use cases, but they are written up and posted on the Categorical Data website. And there's some interesting ones we did with DARPA and some chemists, and stuff we're doing with Uber and Tinkerpop, which you know, Marco would have talked about today, could he have been here. But let me pause there. Any questions so far? Cool. So for the purposes of this talk, it's not really necessary to know category theory, but given as this is the category theory meetup, you know, a lot of the description will be in terms of category theory. And so if nothing else, it's good just to agree on notation and to have formal definitions to refer to later. So with that in mind, the actual introduction to category theory here is pretty light. But what is a category? So a category C in this MathCal font here consists of the following data. So you have a set of objects, that's why we call it ob, in your category C. And that's the first bit of data you give. And now we give more data that depends on that first bit of data, or first set of data we gave. So for every two objects, so for every two elements in that set, we have to give another set. It's called the morphisms or arrows from X to Y. So if X and Y are two objects in the set of objects that we've given, we have another set called the morphisms from X to Y, or the arrows from X to Y. In addition, for each object X, we have what's called an identity morphism. And so we'll use morphism and arrow interchangeably. But basically, you have an identity morphism for every object, right? You have an arrow from X to X for every object X. And then finally, you have an associative function. It's typed in the following way. If X and Y are objects in your category C, then the way you compose is kind of in this backwards order, right? So you have an arrow from X to Y, and then you have an arrow from Y to Z, and you get an arrow from X to Z. So this is how mathematicians will often write function composition in math books. Just be aware that the things here line up kind of in maybe the opposite. It's not X, Y, Y, Z up here. There's kind of a flip in the order, but anyway, we'll see both notations for how to do composition. But anyway, so given the set of objects and then the set of morphisms and the set of identities and the composition function, these all have to be related to each other in a specific way, which is to say that the identity morphisms have to be neutral elements for composition. So if you have F and you compose with identity, you should get back F, right? And then we want composition to be associative. So these are, relatively simple things to want for this data. The intuition here is that you might think of composition as actually composition of functions, right? In which case you would hope that it's associative and has identity. So there is category theory in many ways axiomatizes functions in the same way that group theory axiomatizes symmetries, or monoids axiomatize lists, you might say. So anyway, what are some example categories? So in this talk, we're going to see a lot of categories in the guise of database schemas, but there's a category, there are many others besides database schemas, right? One of which is called set. It has as objects sets. So any set you can write down in some set theory is an object in this category. And then the functions you can write down in your theory are the morphisms between the sets. And since those are functions, they should be associative and have an identity element. Another popular category, especially for people in this meetup, is the category Haskell, or the category Java or Scala or what have you. There the objects are types, and the programs, the expressions in the language that take as input something of one type and emit as output something of another type. Those are the morphisms in that category. So category of sets, popular with mathematicians, category of a programming language, popular with programmers, but there's categories of topological spaces, partial orders are categories. Pretty much everything is a category, which is why it's mathematically such an interesting and useful concept, and why it's the correct data structure to use to achieve universal interoperability among data systems, as we like to argue. So I'll pause there. Next on this slide is a functor, which is a morphism of categories, but let's pause for questions on the definition of category. Questions?
I'll tell you my favorite definition of category.
Sure.
Reflexive, transitively closed multigraph.
Yeah, that's one way to do it. You have to, it's certainly but yeah, there is an interesting difference in the character of the theories between graph theory and category theory, in the sense that most useful categories tend to be infinite. Even the ones that our database schemas present infinite categories, whereas in graph theory, like, you don't really see infinite graphs as much. They tend to be more combinatorial. So there is a difference in how the theories play out. But you're right. You can absolutely think of, or you can exploit the close connections between graphs that have transitively closed edge relations and categories to get a lot of insight into both subjects. Thank you for sharing. Other questions, comments?
I suppose you could add if you're speaking about graphs, that every graph gives rise to a category, a free category.
Oh,
So-
that's true. We'll see that construction in a bit. Yeah, there's other connections between categories, of course, besides just the one mentioned here. For example, every graph induces a particular category called the free category. So there's a lot of rich connections besides just the one that was mentioned now. Absolutely. Sister subjects for sure. Other questions, comments? Okay. So then just to finish off the bit of category theory we need, which is actually a relatively small amount of category theory, what is a functor? So this is a morphism, a homomorphism of categories, if you will. So, a category is defined above the line as just an algebraic structure. And so we would expect a notion of homomorphism of them, right? Structure preserving map. And so in particular, we have that here. So a functor from category C to category D consists of two pieces of data. One is a function. It takes objects of C to objects of D. And then the other, we refer to that as F. So here we're going to call F the functor, and we're going to call the function from objects to objects F, and we're going to call this last bit of data, which is for every two objects X and Y, a function from the arrows from X to Y and C to the arrows from F of X to F of Y and D. We're also going to call that F. Anyway, the definition is not as complicated as it might first appear. Basically, all we have to do is make sure we're assigning objects to objects and arrows to arrows in such a way that identities and composition are preserved. So here we're not really writing down, like when we say id, the identity for which object, for example. So really what this is saying is F on the identity at object X is the identity applied to F of X, for example. So the reader has to fill in some of the little subtleties for themselves, but the idea is that a functor is something that takes each, or I'll put it this way, a functor preserves composition, right? So if you have two things that compose in your source category, and you transform those with F, that should be the same as if you apply composition after you're in the target category. So this is not unlike how in a group, you might also have to preserve inverse, for example. So anyway, yeah, functor is a homomorphism of categories, and there are many functors. They show up everywhere. In this talk, they show up principally as what are called schema mappings. Since our schemas are categories, our maps between schemas will be functors. But another example of a functor that is a functor from the category of sets to the category of sets is the power set functor. So what that does, that function on objects, it takes each set to its power set. And then each function it takes to its image underneath the power set. So details aren't too important, but there are, tons of functors on the category of sets. In Haskell, there's a functor from the category Haskell to the category Haskell that takes each type to the type list of that type, right? So that's a functorial operation that takes types to types and turns to terms in a way that respects these identities here. So in particular, well, yeah, anyway, I'll pause there. Questions on functors before we get into the categorical data aspects? All right. So what is categorical data in a nutshell? So, we usually attribute this to David Spivak going back to 2010, but the theory of what I'm giving here goes back to something called sketches in the 90s, and there's plenty of other people contributed. So anyway, with that disclaimer in mind, the basic idea is this, that we want to define a database schema to be a finitely presented category, which is to say a graph plus a set of path equations through it that denotes a category. So we're going to say these are our database schemas, these graphs with this extra structure on them, an example of which is written down up here. So I'll walk through this in detail, but the basic idea is if we just say this is what a database schema is, can we derive a data migration calculus that is suitable for ETL operations? And if so, is it better or worse than existing calculi like relational algebra or data log or Java or, God forbid, Hadoop, right? And so we have answers to those questions, but fundamentally the idea here that, or at least the way the mathematicians came at this is that, as they said, let's just say a database schema is a category and see what we can, what falls out of that, right? Sort of assume energy is equal to matter and see what happens. So anyway, with that history in mind, what are we seeing on this slide? So this is a directed labeled multigraph at the top above the line here, plus these things that I'll describe later. They're called path equalities. But anyway, yeah, directed labeled multigraph. And so the intended labels here, this is manager, this is employee, this is department, last name, first name, name. So this is intended to be a schema for a database where the arrows represent foreign key relationships. And the additional pieces down here where we get more than just a graph, what makes this a presentation of a category, not just a graph, are these equations between paths. So in particular, this first equation says, if you take the manager loop and then go along the works in loop to get to a department, that's the same as if you just followed the works in foreign key, right? So that's a data integrity constraint. It says that every manager, I have to be a little careful, it's easy to read these wrong. Every manager works in the same department as their employees, which may be a bit of an unrealistic assumption, but is kind of fascinating as a data integrity constraint. It's certainly not something you could write down in an SQL database or even an OWL RDF database, given some limitations of description logic. Anyway, the other constraint here, it says that if you follow secretary and then works, you come back to where you started. So that means that every secretary should work in the same department that they're the secretary for. And so mathematically, what's happening, and I'll get into this on the next slide, is that we can form a category out of this graph from the paths through it, where we equate paths that are equal according to these equations here, or things that we can deduce from the equations here. But to finish out the story at the intuitive level, what we see here below the line is a database on this schema. So mathematically, it's what's called a set valued functor. It's actually a functor from this category here to the category of sets. But it's basically just a set of database tables in the tables of a particular form. So these are relational database tables, but where every table has a primary key column called the identifier, and each edge out of a node is present in the table, right? So if we look at employee, it has manager, works in, last and first going out of it. So they're the columns that are in this table. And then if we have 3 employees, those become the 3 identifiers. So we call relational databases that conform to a directed labeled multigraph like this, we call them as having categorical normal form, as opposed to, you've probably heard of COD normal form or third normal form or what have you. There are ways to relate the two concepts, but anyway, this is what we mean by schema, and this is what we mean by data, and we'll come to find that up at the top here we have a category, and down here we have a set valued functor, and so all the operations from the mathematical textbooks apply to build an ETL calculus. But let me pause there and ask if there's any questions.
Are you going to have any cones or co-cones in this?
So yes and no. So here, in as much as we're describing, or maybe the way to put it is that if you want cones and co-cones, you need something that's not an equation. And so this story becomes more complicated. But in the ETL tool that we've built, we do support cones and co-cones. We have another kind of data integrity constraint that we call an embedded dependency that expresses non-equational things such as that. They actually look a lot like data log. Does that answer your question?
Yeah, that's nice. So that brings you to sketches, which are actually
Mhm.
from the 80s, not the
Yep.
90s.
Oh, there you go. Yeah, I mean,
And
probably the
without,
70s, you know,
yeah,
or, you know,
and
Tarski or something, right? Yeah.
with just the equational stuff, you're kind of at Lavier in 1963.
That's correct. Moreover, we're even less than that, or rather, we're careful that what's above the line here is a finitely presented category and not a finitely presented multi-category, for example. So, and I'll get to this later. There is another story here where, say, we want to talk about things like addition, right, which would conceptually be a multi-edge in this graph, right? From integer and integer together, you get an integer. And that is, so that's, there is in the story I'm telling now, we're actually disallowing even products. So we're not even having Lavier theories. It's just finitely presented categories. But then there is a principled way to add products back to the story I'm telling that preserves the ETL calculus. Anyway, that's maybe a bit more detail than you asked for, but we're, at least for now, yeah, we're restricting to finitely presented categories even, so less than Lavier theories. Other questions, comments? Cool. Okay. Those were good questions. I like getting into the technical nitty gritty. Anyway, here's what the code in the tool looks like, you know, if you enter it as text. Just unary functions, right? So actually that's sort of the giveaway that we're in we're not in a product theory, a la Lavier, right? Everything is unary here. And then the equations, we just use the name of an entity to refer to its identity morphism. So easy to type these things in. The tool, of course, can import them from other, you know, other systems and such. People don't have to write them as text. But what's the math here? So I won't dwell on this too much, but just formally speaking, and the details are all in the papers we published. But we take the graph, the directed labeled multi-graph, and we form what's called the free category. So the objects there are the nodes in the graph, and then the morphisms in that category are the paths through it. But then what we have to do is form a quotient of that category. So we have to equate all the paths according to the equations that we wrote down. And now our objects are equivalence paths of graph, equivalence classes of paths in the graph. Oh, that is a mouthful. And that is the category that the schema denotes. And by denotes, we used the little church brackets here around the schema S to say, you know, so the brackets S is the category and the S is the presentation, the graph and the equations part of it. The caveat here, of course, is that, you know, you might, this formalism might look trivial. It's just, you know, equations between paths in a directed labeled multigraph, but the actual question, does any given equality of paths follow from a set of paths through the graph, in general is undecidable. So you can write down, or you can put like a Turing machine in a schema here. And so, you know, even though this category exists, actually like implementing it constructively on a computer may be impossible. And so a lot of the magic and the reason for the commercialization of the CQL tool is that you know, we're deploying techniques from automated theorem proving to make all this tractable, right? That this is actually a very attractive semantics for a schema, but that because all these constructions using these schemas are undecidable, in practice to do things, you have to apply automated theorem proving techniques. And so that's where the rubber hits the road. Mathematically, of course, you just, you know, none of that matters, and the mathematical story is very beautiful. Anyway, that is what a schema is. I'll pause there. Questions on how we form categories out of schemas, aka presentations of categories? Okay. Right. So then, what are the other artifacts look like? So we just said how to take a schema and get a category out. What we want to define next is a notion of schema mappings, which is like the syntactic equivalent of a functor, right? So you know, this category here is infinite right? It has, for example, the morphism manager and the morphism manager followed by manager and the morphism manager followed by manager followed by manager, right? The category here is infinite, but this graph here is actually finite. And so you can think of this as a syntax, if you will, for categories as a semantics. And so what we're going to define next is what a schema mapping between categories is. And so what that is a function from the nodes of one category to the nodes of another, and the edges of one to the paths of another. And so I'll drill down on this definition later. It's not important to understand the details now. The point that I want to draw home now is that because we're working with, on a computer, these presentations of categories, we're also working with presentations of functors, presentations of natural transformations. We're not working with categories themselves, right? Those are infinite artifacts that are hard to represent on a computer. And instead, you have to work with these presentations of things. And when you do that, you run into issues about undecidability that require automated reasoning to tackle. So that's schemas, and those are schema mappings. I'll pause there and then talk about the mathematical meaning of data in the picture, if there are no questions. So questions, comments?
Got a question about, you said, what was that, primary keys or foreign keys?
Foreign keys. Yep.
Your syntax was making a few more distinctions than you mentioned. So you're distinguishing foreign keys from attributes. What's the difference?
Oh, that's true. That's also a SOP to living in a constructible, computable universe. In particular, the only difference here is that string, we call it a type rather than an entity, because like the intention is that you have a finite set of employees, right? You have a finite set of departments, whereas you have an infinite set of strings. And so right here, I used a ... But in the tool, right, like the way we do have to indicate, right, like, okay, there's going to be infinitely many strings, but not infinitely many employees. And so we break it out here. So that is something I'm pushing under the rug, but it's fully worked out in all the papers, and I'm happy to elaborate on it when we get to the end of the sort of the intro part. But
Okay,
you're right,
thanks.
that's a good catch.
Yeah,
There's more going on here. Yeah. In fact, as we'll see later, you have to be even more careful, because in category theory, all these constructions are defined up to isomorphism, right? And so if you're not careful, that freedom in defining constructions up to isomorphism can actually be too coarse for what you want in data management. And so there's a whole nother body of work we had to do about, like, well, if the category of sets can't distinguish isomorphic sets, but you do need, Bill and Alice to be distinguished from Perkins and Sue, what do you do? So there is a lot that's being swept under the rug, but hopefully the beauty of the sort of the naive approach is a good motivation for studying it in detail. Good question. Other questions, comments? Okay, then I'll finish off the categorical basics. So what is the actual database up here? So we said we said how this presentation of a category creates a category, and we said what a functor out of a presentation looks like. And so what these tables are is they're just a tabular representation of a functor from this category into the category of sets, right? For each node, we have to give a set. And so for employee, we give the set 101, 102, 103. For depth, we have to give a set. We give these two IDs here, Q10, X02, were the department IDs for some reason. The set of strings is this infinite set. That's what it means to give a functor from a category into the category of sets. In addition, each edge has to represent a function. And so this is the connection to foreign keys. So for example, last has to be a function, which is to say a column hanging off of the employee table in a functional way. So this ID column is a primary key, and this is a foreign key into string, right? We have to give an actual function, and it just gets encoded as this table, right? So it's manager is the function that takes employee 101 to employee 103. It takes employee 102 to employee 102. So I guess that's CEO number 1, and then this other guy is CEO number 2 or something, because he also reports to himself. So, you know, the data is a bit made up, if you will. But that is what a set valued functor is just an assignment of sets and functions according to the graph in such a way that these constraints are respected. And so in particular, hopefully, if we actually work out, you know, for each manager where they work in, and then for each employee, right, work out where they work in, that these equations are true. Oops. So, you know, it's easy to check if these equations are true in a model. That's not undecidable or anything like that. And yeah, so anyway, that is what a database is. So we have a category, and a database is a set valued functor, and it can be represented as a set of tables, one for each node and edge, in such a way that the equations are respected. So questions on databases as set valued functors? No. Okay, great. And I'm going to skip the part on what a morphism of databases is, although they'll come up a bit later, but the details are not important. So the basics of how you program ETL tasks using this calculus, it looks like this. So the calculus is based on functors. It's based on schema mappings, right? So we're going to build a sequence of functors from A to B if our task is to ETL data from A to B. It may be more than just one functor. So in particular, what we're going to see is that with each associated with each functor are 3 data transformation operations. But conceptually, to get from A to B, we create a sequence of functors and a sequence of other intermediate categories to connect these things. So here's an example of a functor. And these are on schemas that are new that we haven't seen in this talk so far. So here on the left, the source schema. So this is just a directed labeled multigraph with no equations. So this is a bit degenerate. The nodes are N1 and N2. The types, string and int. And then the attributes or the foreign keys or whatever you would like to call them. We have name, salary, and age. There's a similar schema that we're using as our target. And it's similar in the sense that the attributes are the same, name, salary, age. But there's only one entity, only one table, right? And there's no foreign key F. And so there is a functorial relationship between these things. In particular, I mean, there's several, but the example here, we send string to string and int to int. So, you know, one of the things glossed under the rug is that the schema mappings have to be type preserving. So if you wanted to get from string to int, you'd have to convert string to the int, et cetera. And then the two nodes here, the two tables, N1 and N2, both get sent to N, and then the foreign key here, F, gets sent to the identity path on N. That's what this empty thing here means. And so this is a functor, right? You can check that it sends nodes to nodes and edges to paths in such a way that all those equations are true. And then there's no equations associated with the source or target schema, and so there's nothing to check there that those are preserved. And so anyway, this is a schema mapping between two schemas that we'll walk through some examples of, and then I'll show the tool, and then that's the sort of the intro portion. So questions on what schema mappings are, or rather this example of a schema mapping. All right. So how do we get from schema mappings, functors, to data transformations? So the thing to understand here is that because our schema mappings are functors, and so are our databases, they're just functors in a special category called set, we can actually compose them. So if somebody writes down a schema mapping or a functor F from S to T, and they also give you a database on T, you can turn it into a database on S. So you actually, we get an operation here that goes in the reverse direction of the schema mapping. If the schema mapping is from S to T, there's a very simple way to describe an operation that takes T databases and converts them to S databases. Namely, to answer the query against, to give the set of rows for something in S, right? You just find out where it goes in T and then look it up in your instance. And then that's what you use for your answer. And so this is a very projection-like operation that you get just from composing schema mappings and databases. And we call it delta, and it's defined as composition like this. So I'll pause in just a second, but first let me say where this is going, which is that there is then, or rather this operation of projection is, not enough to do ETL tasks, right? You can't join things with it. You can't union data with it. However, there are two operations that are a kind of inverse to delta. Not actually an inverse, right? You can't invert a lossless or a lossy projection, but a kind of way to freely add data back. Anyway, there are operations that are defined solely in terms of how they relate to this easy projection one, where we get a lot of the ETL semantics. So this pi is defined as a right adjoint, a right inverse, right quasi-inverse to delta. It's what lets us do join. This sigma thing, it's a left quasi-inverse, a left adjoint to delta. It lets us do symmetric transitive closures. It lets us do disjoint unions. And so it's these other operations that are where a lot of the power comes from. But it's this simple operation of projection that has a very easy definition in category theory. Literally just take your database, take your schema mapping, compose them, and off you go, right? That is definitely a distinguishing feature of the categorical sketch-based approach to a relational approach. I'll pause here. Questions? Comments?
Sorry, yeah. Are you going to go into more detail about pi and sigma?
Right. And in particular, the way to do that is through examples. So, here we did write down the definition, right? It is possible to describe it purely at the level of, what does it mean to be a quasi-inverse? But instead, what I'll go through now and conclude with before showing the tool is essentially examples of these data migration operations. And the argument here is that the semantics here is nice and useful, and that you should use these to do ETL tasks instead of SQL, instead of Informatica, instead of Data Tamer, what have you. So with that in mind, the example we're going to start with is actually a little bit different than here. In particular, we're going to remove this foreign key F to start, just to kind of see what happens when there is no connection in the source schema between the two tables. So here the schema mapping looks like this. We still have the same three attributes and two tables, but there is no connection in the source between the two tables. And so the delta F, what does it do? It takes a database, for example, here, one table, right? Since the source of delta is the target of the schema mapping. And it converts that into a database with two tables here on the left, right? Two tables because we have N1 and N2 up here. And in particular, the data gets copied over, but we are actually forgetting the association between Alice and 20, right? So this is an example of a lossy projection, which, maybe you use in practice, maybe you don't, but it's certainly something that you need in an ETL tool, what with having it project data and all. So I'll pause here. Questions on this example? And I'll pause for a little while, because usually this is the first place where the intuition or the rubber hits the road, in the sense that we have a schema mapping up here that goes from left to right, but a data transformation that goes from right to left. And so that can be a tricky intuition to get one's head around. So I'll pause for a few more seconds, and then if there's no more questions, move on to the other example. Okay, cool. So the other data migration operations, what do those look like? So we have the same functor, same schema mapping as before, right? In particular, there's no foreign key here in between N1 and N2. But pi is the right quasi-inverse, right adjoint to delta. And what does it do here? And so what it does is it takes a Cartesian product, a full cross join in SQL parlance. And so in particular, we see Alice and 100 now paired with age 20 with the other age 20. So this is, you want to call this bag semantics, call this set semantics. It's, it's the semantics you get when you have set semantics plus primary keys. It has Alice there and Alice again, right? And so it is nice that we actually get, unlike in sets where cardinalities are not preserved by multiplication, say we do actually get 3 times 3 and 9 here. But this is what pi will do in this case, is a product operation. And one of the things I'm sweeping under the rug a bit is the choice of identifiers in the instance that's generated. So in particular, if we were, say, representing this data on a relational database, or rather, naturally, we might think of this ID in this row as being a pair of 1 and 4. Here, as I wrote it with A, as A. So the way, and the reason I did that is mostly to illustrate that there is, this being category theory, there's actually a choice. There's infinitely many pi operations that they all return the same data, the same name, salary, and ages. They actually differ in the choice of the meaningless identifiers that they put in the ID column, right? So there's another pi that chooses ID 0, 1, 2, 3, 4. There's another pi that chooses ID 1, 4, 1, 5, right? So there's actually infinitely many. And the tool we built exploits that fact to like encode the universal property and other information in the identifiers. Anyway, in this slides, I just made up new ones, but anyway, that's pi. Questions on this operation? Okay. Sigma. So sigma is the left adjoint, the left quasi-inverse. So what does it do here? It does what in SQL is called an outer union, although in SQL with its weird 3-valued logic and null semantics, it doesn't quite do it how category theory says you should. In particular, what should happen here is that we're doing an outer union on tables that are not compatible in the sense of COD, meaning we have to enter in null values. But we want to enter in distinct null values. So in particular, null 1 here is like a fresh symbol that does not appear elsewhere in the database, right? Null 2 is a fresh symbol that's not equal to null 1. So these are called labeled nulls or Skolem variables or what have you. The point here is that they're all distinct from each other. We have to add them freely when we materialize data using this sigma operation. But in this example with the same schema mapping as before, it does an outer union with labeled null semantics. So I'll pause there. Questions on sigma?
Those labeled nulls seem a bit like blank nodes in RDF.
They're probably the same. Yeah. I mean, it's a timeless concept, right? Labeled nulls, Skolem constant, Skolem variable. COD had a name for them. I'm sure RDF blank nodes are like that. I mean, you can't get away from them in knowledge representation, right? Because you're, in the same way you can't get away from null when you deal with pointers. So yeah, I believe that there is a connection there. Other questions, comments? Okay, cool. Then I'll move on to give a few more examples of delta and sigma and pi, and then show the tool, and then wrap up. But before that, just to illustrate like some of the cool stuff you can get just with what you've seen so far that you get out of the category theory, is that because sigma and delta are these adjoints to each other, there's a way you can round trip them. So in particular, if you start with your data that we had as shown, and then we sigma it forward, like as we showed, and then if we delta it backward and like break it back up again, then there is a unique way to embed where we started into where we ended up, right? So this is the union of, right, so there's an assignment, right, that we can set null 1 and null 2 in such a way to make this happen. Anyway, this is a round tripping property that you get from this ETL calculus that we exploit in practice, right, to relate data where it started from where it ended up. But anyway, to conclude here, here's what the example looks like when there is a foreign key in between these tables. And so this is where you start to see more of the power of the calculus. So if there is a foreign key between N1 and N2 here, then if we start on the right and we do a delta, then we remember the connection between name and salary and age as that foreign key. So delta does a lossless decomposition. In the other direction, if we start with data that already is associated like this, that's joinable, both pi and sigma will actually join it. So both the join and union semantics coincide when there is a direct connection along a foreign key like this. And so you get this very nice, what I would argue is the semantics you would expect, right? That given this schema and this schema and this mapping, there's really only 3 natural ways to move data around, and that we just enumerated them here. So anyway, that is the sort of the basis of the story. What I'll do next is like describe how the tool differs from that story, show it a little bit, take questions, and then conclude. But for now, is there any questions on this example here, how delta and sigma pi operate in the presence of a foreign key? Cool. Yeah, so some of the practical notes, what comes up in practice. So in practice, these schema mappings, these functors are actually a little bit, they can be hard to program. It turns out that when you package together pairs of schema mappings, like the delta with the pi and the delta with the sigma together, you get an alternate basis for data transformation that looks like SQL syntax almost. So we call these things queries. They're both available in the tool. They do the same thing. In this case, sort of the source and target are flipped, but basically they evaluate and co-evaluate as you might expect. So the tool lets you create schema mappings and delta sigma pi them back and forth, and also like you can build an abstraction on top of that that looks like SQL, that looks like a query, and you can run queries forward and backward. So that's one key difference in practice. There's a few others, but I think what I'll do is go ahead and bring up the tool, play around with it a bit, and then yeah, that'll be that. So I'll stop the share while I get the other thing up and running. Any questions while I do so? Okay. All right. So let me see. I'm going to share the entire screen here just because we get pop-up windows. So here is the categorical query language IDE. This is the open source version that's available for free on categoricaldata.net. Comes with a bunch of built-in examples, each of which does not sweep under the rug all of the nitty-gritty details about like what are strings versus integers and stuff like this. So basically you end up writing down things that look a lot like what we talked about in the slides, but that are subtly different, right? So for example, up here we said the string is a set of all Java strings, and plus is like how Java does plus. So there's sort of the bindings of our formalism into a programming language we didn't talk about in the talk, but the tool has to deal with. And so, for example, here is just some data on a schema, right? So here's, here's employee with the attributes listed, attributes listed as opposed to written as a part of the graph. Excuse me. Manager in the circle. Here's an instance on it, right? Bob, L, Carl. Here we've chosen identifiers 0, 1, 2, 3, 4 that are kind of hard to read. But there's, that's just a sort of a graphical type of thing. What else can I demonstrate? So schema mappings. So here's here is an example where we have a schema that talks about amphibians, land animals, and water animals, where a amphibian is a land animal and a water animal. And we want to integrate it and figure out who all the animals are. So this is a bit of a tricky operation in, say, SQL. You might have to, it's quotienting a set by an equivalence relation. Anyway, what you do in this tool is you create a schema mapping from one schema to another, which is actually just an inclusion. And then you run the sigma operation. And so, if you start with a schema that looks like amphibians and land animals and water animals like this, and you're moving into a schema where you also want to have all the animals together, but you want to make sure that you're not double counting the land animals and water animals. You just create an inclusion mapping. If you start with data that includes geckos and frogs and humans, where geckos and frogs are the things in common, you do the data integration. Oops. You start with you start with geckos and frogs in common, and then you do the data integration, and you find you have 7 animals. They are and here's the provenance, right? Animal 1, follow its foreign key and get to this water animal. So that the provenance takes some getting used to. It's sort of all encoded in a machine representable way. But anyway, the point here is that we started with 5 land animals, 4 water animals, and 2 amphibians. And through just an inclusion schema mapping, right, like trivial schema mapping, ended up on a database where we have 2 amphibians, right? 7 plus 5 plus 4 minus 2. So it figured out how to get rid of the double counting based on the schema in the target saying that each amphibian is the same animal. So anyway, that's a data integration scenario expressed in this tool. There's all sorts of stuff. There's probably not time really to cover too much more, but let me show one more bit because this can save programmer error. The tool, because it's based on category theory, gives you strong guarantees about the programs you write. So for example, if we're building a dating website that has men and women and they each have favorite books and the men can pay for the site, and we're trying to build a reporting warehouse where we have the paying good matches, right? The men and women who match on the same book and who the men are paying, you can write a query that looks like SQL to populate the report, right? Loop through the men and women, find where the favorite book matches, blah, blah, blah. What's cool about doing this in category theory is that if you make a mistake, even if you don't have data around, right, the tool can check your work, right? And down here in particular, it says, oh, if you're in paying good match and you missed a join condition, right? I can't deduce that from your paying good matches, your good matches have enough stuff to guarantee a foreign key, right? So there's an element to saving programmers time in building ETL flows here based on exploiting the data integrity constraints that are the extra stuff that makes a category, not a graph. Anyway, a bit of a rant, but I will pause there. Any questions about CQL, the tool, or anything like that?
Sure. How about like distributed databases? Do you have a query optimizer at all? And if we describe 2 databases, can you glue their schemas together and then do queries over both of them?
Yes. So the way the open source prototype works is that it can import data from 60 different SQL vendors, RDF, JSON, XML, blah, 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 process it in memory, and then emit back out to those same vendors, RDF stores, what have you. So the open source tool is designed to be the data processing engine. And so there are commands in the tool, right, to say export data over a JDBC connection, since the tool is written in Java, or import data over a JDBC connection, right? So it does interoperate that way. The commercial version of the tool works by code generation, right? Because you probably wouldn't want to pipe 800 petabytes worth of information on your laptop, process it in memory, and then spit it back out, right? What you want there is for this program to be compiled into your IT infrastructure, say Spark or Hadoop or what have you, and then executed there. So that's what the commercial version of the tool is focused on. The open source one, it does run in memory, but it has no problem processing like 10 gig data sets or any within a few minutes. It's sort of reasonable performance for I don't know, the kind of data wrangling you do on your laptop in SQL, say. And there are formal guarantees about its performance relative to SQL and whatnot. Was that a helpful answer?
Yeah, sounds great, man.
Okay, cool. Yeah, also happy to elaborate offline. Like if you have a particular scenario in mind where you needed to glue two databases together, say in a way that, or there's a other alternatives too besides what's I've described so far. So yeah, happy to chat about that offline if you have a particular project in mind. Other questions, other comments? Yeah. Cool. Alrighty. Then with that, we'll call it a day. Like I said before, our second speaker had to cancel because the power got cut to his house. But I think we'll probably try to bring him back. He has a pretty cool application of category theory to distributed databases. In particular, the connection between this tool and what our speaker was going to talk about is that tool can be a back-end implementation strategy for ours, for CQL. So we'll get him back at some point, but for lack of a second speaker, yeah, I'm inclined to call the meeting halfway through and then see you all next month, or possibly earlier if we can get Marco rescheduled for his talk. So unless there's any final questions, I'll go ahead and end the meeting now.
All right, thanks, man. Thanks a lot.
Right.
That was a lot of fun.
Yeah, always a pleasure. Thanks, everybody. Oh,
All right.
some people in chat here. Bye. Yep. Bye.
All right, thank you.